Hi everyone. In our last few videos, we've been going over 2 by 2 systems of linear equations. Now, you can have linear equations effectively, or systems of linear equations, effectively as large as you want. But now we are going to look at 3 by 3 systems of linear equations. All right, and that's probably going to be the largest systems that we'll take a look at in this class. But let's go ahead and see if we can solve one of these. So the basic principles remain the same. The idea is that you want to try and eliminate as variables so that you can isolate one variable by itself and solve one of the variables. Okay. And when you have a 3 by 3 system, the first thing you probably want to do is try to reduce it to a couple of 2 by 2 systems. That's usually the strategy you want to take here. So let's go ahead and do that. So if we look at each of these equations in this first example, the one that sticks out to me that would be the easiest to try to eliminate to one variable to make it a 2 by 2 system would be these first two equations. All right. So if we were to add equation 1 to equation 2, that would probably eliminate our y variable. So let's go ahead and do that now. So if we have negative x plus 2y plus 2z equals 7 plus 2x minus 2y minus z equals negative 6, if we add negative x to positive 2x, we'll get x. 2y minus plus a negative 2y gives us nothing, so we can leave that. And if we add 2z to negative 2z, we get positive z. And z plus a negative 6 gives us 1. So there we go. We have reduced these first two to an equation involving just x and z. So now, since we've eliminated the y variable, we now have to commit to that y variable, at least for a minute. And we have to pick a different set of equations and eliminate the y variable, okay? So it can't be the first two equations again this time. So let's do maybe the first and the third this time. Okay, we do the first and the third. If we were to multiply this top equation by 2, all right, so let's do that. So we have 2 times negative x plus 2y plus 2z equals 7, okay? And we're going to add that to 3x minus 4y minus 2z equals negative 9, all right? That's going to give us here, we'll have negative 2x plus 4y plus 4z equals 14. And I will add that to 3x minus 4y minus 2z equals negative 9. So now we can eliminate this y variable quite easily, because we'll see adding 4y to negative 4y will eliminate that. So negative 2x plus 3x gives us x. Okay, and then we have 4y plus negative 4, that goes away. And then 4z minus 2z gives us 2z. Okay, and we have 14. Minus 9 gives us 5. So now we have x plus 2z equals 5. So now we can take each of these equations and we can add them to, or try to add them together or subtract them to see if we can eliminate one of those variables. So we have x plus z equals 1, and we have x plus 2z equals 5. Okay, so let's go ahead and multiply the top equation by negative 1. So if we multiply everything in top equation by negative 1, we'll have negative x minus z equals negative 1. And we're going to add this to x plus 2z equals 5. Adding these two together, the x's will go away. And we have negative z plus 2z. will give us z, and negative 1 plus 5 is 4. So we have that z is equal to 4. So from this whole system of linear equations here, we've been able to find one of the variables. And now what's nice is, since we know that z is equal to 4, we can also very easily find x, because we can take this z, and we can plug it into any of the two equations that we just reduced here. So I'm thinking we could take this z and plug it into x plus z equals 1. So we'll have x plus 4 equals 1. So now we can take 4 away from both sides, and we get x is equal to negative 3. Okay, so now we have been able to find x and z. So we know that x is equal to negative 3 and z is equal to 4. So now we can take both of those values and plug it into any of our initial 3 equations and see if we can find the overall solution. So let's take that. We can maybe plug it into the first one. None of these look like they're any easier than the rest, so we'll just do the first one. So we'll have negative x, or we'll have negative 3 plus 2y plus 2 times z, or 2 times 4, is equal to 7. Okay? So now we have this, that this will reduce to, after we deal with the negatives here, we'll have 3 plus 2y plus 8 equals 7. Combining like terms will give us 11 plus 2y equals 7. All right, so now we can take 11 away from both sides. All right, and we'll have 2y is equal to negative 4. So we can divide both sides by 2, and we have that y is equal to negative 2. So our final answer is going to be x equals negative 3, y equals negative 2, and z is equal to 4. So not too bad. It's really nothing new, nothing we haven't seen already. Just a lot of steps, and unfortunately, a lot of places you can make a mistake. So be sure to be careful as you're going through and solving these, because it is very easy to make a mistake. So let's look at another example, maybe one that might be easier to solve, might not be, depending on how you look at it. But in this one, we have this system of linear equations here. Okay, it is sort of an implied 3 by 3 system because we do have 3 variables technically present for all of them. It's just some of them have a coefficient of 0. Okay, so now all we have to do is see if we can use substitution maybe to solve some of these. All right, so the first step I want to take here is to go ahead and solve the middle equation here for y. All right, so with this one, if we add 2z to both sides of the equation, we'll get y is equal to 6 plus 2z. So now what we can do is we can go ahead and plug this y value in to our third equation here. Okay, so doing that, we have 4x plus 3 times 6 plus 2z is equal to 20. Okay, so let's go ahead and distribute this here. So you have 4x plus 18 plus 6z, after we distribute this 3, is going to be equal to 20. So let's see if we can maybe take 18 away from both sides. and we'll get the two-variable equation 4x plus 6z is equal to 2. Okay, so now what we have is we have eliminated, uh, let's see how we can do this. Okay, we have 4x plus 6z equals 2. We can take this and we can now combine this with the first equation here. Okay, so we have 4x plus 6z equals 2, and then we have x plus 3z equals negative 1. So 4x plus 6z equals 2. Sorry, this is my first time doing this one as well. So one of the cool things about these equations is really these systems of equations is it's kind of a choose your own adventure game. There's a lot of different ways you can approach this, and hopefully, if you do everything correctly, you will end up at the same place in the end. So we can combine this one with our first equation here. So we'll bring this one down, and we'll get x plus 3z equals negative 1. And now let's see if we can go ahead and eliminate one of these variables. So here we can eliminate looks like maybe the x variable. Really either one will be fine, but I'm going to choose the x variable. So we're going to multiply the bottom equation by negative 4. And that's going to give us 4x plus 6z equals 2. Draw a line here so we don't get confused. 4x plus 6z equals 2. And then we'll have negative 4x minus 12z equals positive 4. Okay, we got that from multiplying 3z by negative 4 and negative 1 by negative 4. Let's add these two together. So 4z plus negative 4z is 0. 6z plus negative 12z is negative 6z. And then we have 4 plus 2 is 6. So if we divide both sides by negative 6, we end up with z being equal to negative 1. Cool. And now what we can do is we can take z equals negative 1, and we can plug this back into any of the equations that have a z in it in our initial set of equations. And we can solve for the other variable. So I'm gonna pick let's do the first equation. So we'll have x plus 3 times z, or 3 times negative 1, is equal to negative 1. This will become x minus 3 equals negative 1. We can add 3 to both sides, and we'll get x is equal to, x is going to be equal to positive 2. Okay, so we have x is equal to 2 and z equals negative 1. And now in this situation, we can go ahead and take our x value and our z value. Let's see, what can we do here? Oh, I guess what we can do here is if we want to solve for y, we can take our z or our y value, and we can plug it back into the appropriate equation here. All we need to do is solve for y. So I'm thinking we could take the z value again and plug it into this second equation. All right, so we have y minus 2 times z, or 2 times negative 1, is equal to 6. Or we have, this will reduce to y, looks like plus 2, because negative 2 times negative 1 is positive 2. So y plus 2 equals 6. We can take 2 away from both sides, and we get that y is equal to 4. Okay, so we get x equals 2, y equals 4, and z equals negative 1. Okay, so when it comes to solving these systems of linear equations, whether they be 2 by 2 or 3 by 3, one thing that you really all you really have to remember as you're doing this is remembering the rules for trying to eliminate variables. You can add equations together, you can subtract them, you can multiply the equations by some constant number, and then add and subtract them. And really the whole goal as you're doing this is to try and eliminate variables as much as you can to isolate at least one of the variables. Because once you've isolated at least one of the variables, it makes it very, very much easier to solve the overall system. So again, as always, if you have any questions about this, please feel free to let me know, and I will be happy to help you out.